Let's introduce now the so-called reproductive numbers. These are very important indexes for understanding an epidemics, and they can be derived directly from the SIR model that I showed you before. First of all, let's introduce the effective reproductive number, also called RT or RF. There are many ways in which you can find it on literature. This number derives directly from the ratio between the incidence rate, that is the flow, that the increase in numbers of the epidemic, and the recovery rate, that is the speed at which people recover, and so they are removed from the infectious compartment. And so you can see here that we have the incidence rates above and the recovery rate below, and after some mathematical reformulation, we can show that the effective reproductive number is just the ratio between beta and gamma, that is the transmission rate and the recovery parameter, multiplied by the fraction of the population which is still susceptible. So the effective reproductive number describe the trend of the epidemic at every given time. So it can tell us if the epidemic is growing or is shrinking. And it has also a nice interpretation as the number of people that an infectious person can infect before himself or herself recovers. So for example, if we have a effective reproductive number of 2, it means that on average an infectious person is able to infect 2 more people before recovering, and so not to be able to infect anymore. So if this number is above 1, it means that the epidemic is still increasing, and on the opposite, if it's below 1, it means the epidemic is decreasing, is shrinking. We can have a situation in which the number is 0 or close to 0. That it means that we have a steady state in the epidemic, which is usually is not maintained long in time. There are many ways in which we public health officers can control the epidemic by understanding the reproductive number. So by looking at the question, we can understand that the reproductive number can be decreased by impacting the force of the infection. That is either by public health intervention, lockdown, and so on, or by changing behavior. Again, as I told you before, lambda is strictly related to beta. And so we either want to decrease the number of contacts, or we want to decrease the probability that a contact will create an infection. On the other hand, we can work on the number of susceptible, and this can be done either by vaccination, or this can happen naturally by the immunity that builds up in the course of the epidemic. And finally, we can also work on the recovery rate by, for example, pharmacological solutions, in order to decrease the period in which infectious people can infect other people themselves. For example, this is one of the most effective ways in which AIDS, HIV disease, was controlled by using antiretroviral agents that decrease the infectiousness of affected people, even if actually they don't decrease the length of the disease. From the effective reproductive number, we can also derive the basic reproductive numbers. This number is the effective reproductive numbers if all the population is susceptible. It's quite simple to derive. We just put the number of susceptible equal to the population minus 1, that is just inserting an infected person in a totally susceptible population, which means that S over N it's actually equal to 1. So we can remove it from the precedent equation, and therefore the basic reproductive number can be described simply as beta over gamma. You can find the basic reproductive number written as R0 as R0 by sometimes you can heard it called also R0. So very similar to the effective reproductive number, this index tells us how many people an infectious person can infect in a totally susceptible population before recovering. And it's also very interesting because it tells us the invasive potential of a pathogen in a specific population. It's very important to stress the fact about the specific population, because the same pathogen can have a really different R0 values based on the population. For example, the same pathogen can have a different R0 value in a preschool children class, in which there are a lot of contacts, than in a office, or in a city. And also between countries, you can have the same pathogen which have a really different spreading capability in, for example, northern countries, in which the density of population and level of contacts is low, compared to the southern countries of Europe, for example, a market in Naples, in which the population density and the level of interaction is much higher. From the reproductive numbers, we can also derive something called the epidemic threshold, which is also very important for infection control. The epidemic threshold is the state of the system, of the epidemic, in which the number of cases start to decrease. That is, reminding the SIR model, the moment in which the I over the T is lower or equal than zero. After some mathematical reformulation, we can see that this situation is met with two conditions. Either when you don't have any infectious people anymore, or more interesting, when beta multiplied by the fraction of susceptible minus gamma is lower than zero. That is, the creation of new cases is lower than the removal of these cases from the infectious compartment. But in which situation does this condition happen? Well, after some mathematical reformulation, we can show that the epidemic threshold is met when the fraction of susceptible in the population is lower than 1 over R0. This is really important from the point of view of controlling infectious diseases, and it just tells us that if the epidemic, if in a certain population we have a fraction of individuals which is lower than 1 over R0, then we can expect the epidemic to decrease and disappear by its own. To make a simple example, if we have a disease with R0 of 2 in a certain population, then it means that the epidemic threshold 1 over R0 is 0.5. So it means that if less than 50% of the population is susceptible, the epidemic will start to decrease by itself. Or if we introduce a pathogen in a population which is already by itself susceptible to less than 50%, for example, by previous immunity, then again the epidemic will never leave off, and we won't see a big outbreak. If you think about it, this is what happens with seasonal flu, in which we have variants every year, but the variants never create a big outbreak because most of the population is still somehow immune. Of course, it's not totally immune, otherwise we would not observe any new outbreak at all, but there is some level of immunity, so we observe small outbreaks. Connected to the epidemic threshold, we had the so-called herd immunity threshold, which is just 1 minus 1 over R0. This threshold tells us that if the level of immunity, in this case, recovered over the total population, remember that in these simplified models, we assume that people that recovered are totally immune, like for measles. If this ratio is above the epidemic, the herd immunity threshold, it means that we want to observe a new outbreak if we introduce the pathogen in the population. And this can happen either by natural immunity, as I said before, or by artificial immunity through vaccination. So in this picture, I show a series of herd immunity threshold relating them to the R0 of various diseases. Maybe you have heard that for measles we need vaccination coverage higher than 90%, and this is due to the fact that measles has an extremely high R0 value between 12 and 18 depending on the population. And so epidemics can be stopped only by having a very high level of immunity in a population. While instead for seasonal flu we need a level of immunity which is much lower, because it's not extremely infectious pathogen. You can see also COVID is more or less in the middle, depending also on the variant. Here we don't have Omicron because I made this slide some time ago, but Omicron is quite big, quite larger, if I'm not wrong, between 8 and 10, going by heart. This plot also shows us something interesting from the evolutionary point of view. We can see that the diseases which have the highest R0 are usually diseases which are not lethal, like measles, mumps, chickenpox. This is related to the fact that these diseases, this pathogen, co-evolved with humankind in order to maximize their probability of spreading, and this probability is increased if they don't kill the host. On the other hand, we have seasonal pathogens which are not very infectious, but because they mutate very fast. And mutation it's more commonly doesn't create an advantage in the spreading of the disease. In the middle, instead, still close to the lower end of the required immunity, we have very deadly diseases instead, like Ebola, diphtheria, SARS. This tells us that a pathogen that is very deadly usually has also a very smaller R0, because the duration of the disease is shorter, because people die before being able to infect too many other individuals. Of course, this have to be the case, because if we had a very deadly disease with a very high R0, probably humankind would have been wiped out already. And I mean, it's not the case. It's not given that this won't happen in the future, but usually it's quite rare. One final insight that can be derived from reproductive numbers is the final epidemic size. It can be shown with some reformulation of the SIR model that the final size of the epidemic, that is the total number of people here marked as recovered. Actually, not the total number, but the total fraction of people that have met the disease before the epidemic dies off, is related to the number of susceptible people at the beginning of the epidemic. Here, the beginning is marked as 0, while the end is marked as infinity, and to the reproductive number of the pathogen. This is called a transcendental equation. It's quite hard to solve, and that's why I won't go into the details of how to solve this equation. But what does this mathematical formulation tells us? So one of the insights is that by definition an epidemic never hits 100% of the population, because this formula cannot be equal to 1 by definition. And this means that even with a very infectious disease, the disease will never infect all the population, because the number of infectious people will decrease faster than what is needed for the epidemic to infect everyone. Also, as I said before, the other insight is that the final size of the epidemic, so the cumulative number of infected people, is strongly related to the initial condition, that is the natural immunity of the population, either natural or vaccination immunity, and the invasiveness of the pathogen, represented by R naught. Okay, in the next lessons, we will see some extension of the basic SIR model to see what happens if we use more compartments or if we have a more heterogeneous population.